Okay, we're taking vectors into the third dimension now, and we're just going to have a look at really nothing new here. We're just going to look at how to represent vectors in 3 dimensions, and we're going to look at finding the unit vectors and the magnitude and all those same things that we did for 2 dimension. In 2 dimensions, we're going to do in 3 dimensions. So that's what this lesson is really going to be about. Nothing here to get too worried about, because it'll look fairly familiar. So we're just gonna show really that in 3 dimensions things work in the same way. Now, I suppose one thing that you might be thinking is perhaps something a little bit different is the how to represent these points. Because we're very good at we're quite straightforward representing points on a 2-dimensional plane, as that's what we draw on, but how to do it in 3 dimensions, it gets a little bit more difficult, well, quite a bit more difficult to comprehend. So firstly, we've got another axis. We've got a z-axis now to contend with. So the z-axis is the vertical axis. So I'm just going to draw here a z-axis, and then we have an x-axis. So it looks sort of, I suppose, might be sort of 120 degrees around from the vertical axis, and then another 120 degrees around. We don't need to measure it, but that's kind of the idea. And we've got the origin in the middle there, and our axes are labelled like so. So that's our z-axis. This would be our x-axis, and this would be our y-axis. Now, it doesn't really matter actually if we move them all around. It just matters that they go in the x, y, z clockwise sort of order, like x to y to z in that way. And then we think, well, 3, 1, 2 then, well, that's 3 in the x and 2 in the y, and these show us the positive. These are the positive axes, so you can see we've got the origin here 0, 0, 0. Now, if we're going to go through and into the negatives, then that's the other side of the axis, if you like. So 3, 1, 2 for p, well, that's just 3 out of x and 1 out here for y, and then it's up off the page by 2. Quite difficult to represent. So what we're going to write down now is we're just to do some examples. PQ in component form, so that would be, so I'll just do that over here. PQ will be, so no different to what we were doing. We're taking Q, the x coordinate of Q, and subtracting the x coordinate of P, so it'll be -1, -3. In component form means we're up like this. 1 to 3 is a rise of 2, and 2 to 1 is a drop in 1. So there's my PQ in component form. Now we're going to do the same for PR, but we're going to write it as a linear combination of the unit base vectors, which are I, J, and K. But firstly, I'm going to write it in component form. So PR is going -3. It's going from 1 to -1, so that's -2. And it's going from 2 to -1, so that is also -3. So there's my PR, and in unit base vector or linear combination of unit base vectors form, that would be -3i, -2j, -3k. Okay, our next example, given these vectors, u equals, so these are in the linear combination of base unit vector form, we're going to convert them to component form. So u will equal, so we're just rewriting in component form, -2, 3, 1. Just getting some more practice at converting between the two forms, -1, 2, and -3, just looking at those coefficients of I, J, and K. Okay, so U plus V, once we've got in component form, I guess fairly straightforward. Are we writing in component form? It doesn't tell us. I suggest that perhaps we'll be just representing our answer in this format, so u plus v. So u plus v will be, let's do u plus v firstly. That's going to be -2, so it'll be -3i, just collecting those base unit vector like terms, if you like. 3j plus 2j, so plus 5j. And then we've got k minus 3k, so minus 2k. Minus 3i plus 5j minus 2k. That is for u plus v. Now for 2u minus 3v, we'll have -4i plus 6j plus k. And then we'll need to subtract 3 lots of v, which will be minus 3i plus 6j minus 9k. So putting together -4i plus I, so that'll be -i. 6j minus 6j, so that's the j's are gone, and we've just got k minus -9k, which is plus 10. Plus 10k. You probably picked up my error here, didn't you? So 2u is, I've just left that at k, so that should be a plus 2k. So 2k minus -9k is plus 11. Okay, so -i plus 11k. And finally, 3u minus v, which will be 3 lots of, right, so u minus v, we're going to go -2i minus -i, so that's -i. 3j minus 2j, so that's plus j, and it's k minus -3k, so that's plus 4k. And we run that, distribute that 3 through, and we get -3i plus 3j plus 12k. Okay, we have a vector in 3 dimensions, 1, 2, 3. Its name is v. And we need to determine in component form the unit vector. Remember the notation, v with a little hat above it, in the direction of v. So the unit vector v, v hat. So we firstly need to establish, do we not, the magnitude of v. So the magnitude of v in 3 dimensions is 1 squared plus 2 squared plus 3 squared, the square root thereof. So the square root of 1 plus 4, 5 plus 9 is 14. So therefore, the unit vector v will be equal to 1 over the square root of 14 by 1, 2, 3, which we can write as 1 over square root of 14, 2 over square root of 14, 3 over square root of 14 as a unit vector in the direction of v. Okay, so the second part to this example asks for the unit vectors parallel to v. Right, so let's just think about the difference there. So the difference here is that we're not after the unit vector in the direction of v, we're after the unit vectors parallel to v. So the only difference here is that we're okay to go in both directions. So this will be simply plus or minus 1 over root 14 by 1, 2, 3, which we can then write as sort of plus or minus, if you like, and then this whole shebang here, 1 over root 14, 2 over root 14, and 3 over root 14, and just a plus or minus sitting out the front of that. Okay, third part to this example is we are chasing the vector with magnitude 7 in the direction of v. Okay, so we know that the unit vector v, well, that's equal to 1 over the square root of 14 by 1, 2, 3. So that means that the vector with magnitude 7 is going to be, so that's 7 by the unit vector v is going to be 7 over root 14, 1, 2, 3. And we're just careful to note that it's in the direction of v, so it is that direction, it is that positive version. So we would write this out as 7 over root 14, 14 over root 14, and 21 over root 14. And I think that's about it. I know, maybe one more example. Okay, final example, and as ever, good idea to pause, do, play. So that by that I mean pause the video, do the example if you feel like you can, and then press play to check your answer. So we've got 2 points, A and B, in 3 dimensions. Find the coordinates of M such that, so you understand that this point A could be written as a vector as OA, right? And it could be in component form like so. This is the same idea where O is the origin as giving it as a point. So as long as you're comfortable using both. Right, what's going to happen here? The coordinates of M such that AM is equal to MB. Well, we need to bring M into play, don't we? So M's got coordinates X, Y, and Z, like so. And so therefore, in this case, all right, so AM, the vector, is going to equal, well, it's going to equal X plus 1, Y minus 3, and Z minus 5. Right, that's AM. And MB, so that's going to be, all right, we're starting with B and we're saying 3 minus X, negative 5 minus Y, and 1 minus Z. All right, now AM has to equal MB, so we've got to make these two here equal. So let's do that. So X plus 1, so these two are, so if you like, so AM is equal to MB. So therefore, what that means is that my X coordinates, they have to be equal. So X plus 1 has to equal 3 minus X. So from that we get, therefore, the X, 2X, beg your pardon, 2X is equal to 2. So therefore X is equal to 1. We also get, don't we, that Y minus 3 must be equal to negative 5 minus Y. So therefore 2Y is equal to negative 2. And therefore Y is equal to negative 1. So that's my Y solution, and Z will be found by taking Z minus 5, making that equal to 1 minus Z. So therefore 2Z is equal to 6, and Z is equal to 3. So therefore, what can we say about M? Therefore M has coordinates 1, negative 1, 3. Okay, now if we have a look at A and B, and if we'd taken A negative 1 plus 3 and put that over 2, and if we'd taken 3 and we'd added negative 5 and put that over 2, and if we'd taken 5 and added 1 and put that over 2, this is looking like a midpoint formula, isn't it? So this would be 1, 3 plus minus 4, that would be minus 1, 5 plus 1 is 6, divided by 2 is 3, 1, negative 1, 3, and of course that is what we've got with M. It's the midpoint of AB. Okay, let's go to exercise 11G now. And I think on a quick glance, that looks like it's good for all questions.